Oh, awesome. Okay. Thank you. So the next speaker is Jacob Steinhardt. Jacob is an assistant professor in the Department of Statistics at UC Berkeley. Jacob actually got his PhD in computer science from Stanford, working with Percy Liang. Uh, Jacob is not an outsider to TCS. He has done a lot of nice work, both in the theory and practice of reliable and robust machine learning. And he's interested in designing machine learning systems that are reliable and aligned with human values. So Jacob is going to tell us about some of his recent work in the space on robustness and generalization. Go ahead, Jacob.
Cool. Thanks, Arvindan, and thanks, Chris, for the very interesting talk right before. So I'm going to be kind of talking about a combination of kind of empirical and theoretical results, and specifically trying to think about how empirical observations can inform the kinds of theoretical kind of assumptions and settings that we apply, and maybe even which inequalities or bounds are kind of safe to use or not safe to use based on whether they're kind of empirically tight or not. This is based on work with my student and postdoc Alex Wei and Wei Hu. Although a lot of the phenomena and results I'll be talking about are really building on the work of many others and have been pointed out by many others. So think of this as also kind of a general overview of this field. So I guess just to say kind of what we're going to be talking about, the kind of overall motivation here is to understand basically how or why do deep learning models generalize. And we might mean two things by generalization. The first would be generalizing just from training data to test data that is still drawn independently for the same distribution. But we can also talk about generalization from some in-distribution data, which I'll usually abbreviate by IID, to out-of-distribution data. Which I'll denote by OD. And so maybe the first 2/3 of this talk is going to be about this first question, but the last third we'll talk about the second question. And okay, generalization is kind of difficult to study. Deep networks are kind of a difficult object to work with. And so an emerging approach to try to get at this question is basically to say, okay, I'm going to just ignore the nonlinear aspect of neural networks and mostly focus on just the fact that they have lots and lots of parameters. And so what this means is that we kind of approximate deep neural networks by high dimensional or overparameterized linear models. And so I don't want to claim yet that you should necessarily buy this approximation. I think, in fact, that this approximation is good in some ways, but bad in some other ways. One way in which I think it's very clearly bad is that if you, I mean, I guess even just, if you look at Chris's talk, it's kind of clear that there's a lot of like emergent and very real structure in the latent activations of neural networks. They're really, feature learning actually does happen. The features you end up with at random initialization are very different from the features that are learned over the course of training. On the other hand, in some settings, such as if you've kind of already learned features from pre-training and you're trying to understand how fine-tuning works, this might work better. Also, some phenomena, such as double descent, actually can be explained in terms of linear models. And so this isn't an approximation that kind of solves everything, but it can actually explain a lot. And I think it's useful to understand what things it can and can't explain. And so in this talk, what I'm going to kind of go over first is just the kind of basic generalization theory. for linear models. And I guess I should say for high dimensional linear models. And actually, it turns out there's lots of analyses of these. There's a lot of variations on how to analyze these models, although they have a lot of commonalities. But some of the commonly used inequalities that people use to kind of simplify analyses here turn out to be empirically very loose. And so we'll talk about a couple empirical obstacles to the standard theory. And by this, I mean that the kind of error terms or upper bounds that you get if you're not careful and apply some things that look fairly innocuous actually become vacuous. This comes down to essentially two issues. One is that the norm of the parameters that are kind of represented in these models empirically turns out to essentially be infinite. And so any bound that depends on a parameter norm is immediately entirely vacuous. The other issue is that the empirical and population covariance matrices in linear regression in the regimes that you would actually care about turn out to not approximate each other. And so if you kind of assume that these are close to each other, then you're kind of only looking at regimes that are not sort of optimal in the sense that you could have tuned your hyperparameters, such as your regularization strength, in a better way to achieve better performance. So I'll talk about those both in a lot more detail later, but that's to kind of preview these obstacles. And so having kind of spent a while with my students trying to understand these, we've kind of found that at least the only way that we've been able to find around this is to actually use random matrix theory. And so it turns out that if you kind of apply some random matrix theory correction terms to this basic theory, you end up kind of rediscovering this very old method called the generalized covariance estimator. This was first kind of proposed heuristically by Craven and Waba all the way back in 1978. And it turns out that it can be understood as a kind of random matrix theory correction to kind of the basic generalization theory for linear models. So this is going to be kind of the first part of this talk, is kind of trying to explain what you normally do, explain why it runs into some issues, and explain how to fix it. Once we kind of have that perspective, which again, remember, is all about this kind of generalization from train to test, then we're going to apply this same kind of framework to try to understand OOD generalization from this same linear perspective, and find that it can help inspire an actually useful estimate of the outer distribution risk, even for actual large-scale empirical nonlinear deep networks. Okay, so let me dive in, and let's start with talking about overparameterized linear models. So let's start with just a little bit of setup to make sure that we're on the same page. So what's the kind of setting here? So the setting here is we're trying to learn a linear model. So we observe samples x1, y1 up through xn, yn that are drawn from some population distribution p star. So p star is basically a distribution over pairs of vectors and scalars. So all of these xi are p-dimensional vectors. All of these yi are scalars. And generally, we're going to be assuming what we mean by the high dimensional setting is that P should be much larger than N. Or potentially even P is just infinite, and then we kind of think of these as embedded in some kernel space. I'm not going to worry a ton about kind of the epsilons and deltas of infinite dimensional Hilbert spaces. And so I'm mostly just going to think of P as some very large number that's much larger than N. This also kind of matches empirical deep learning models where P might be in the tens of millions, N might be in the tens or hundreds of thousands. And so, maybe that's the regime you should be thinking about. And so the kind of underlying assumption that makes things linear is that each of these yi's is related to xi by taking the dot product with some parameter vector beta star that is some sort of true parameter vector that we're trying to learn, and then adding potentially some noise epsilon I, where we assume that the noise is zero mean. And so our goal then is basically to obtain some estimate, beta hat of beta star, that has low generalization risk and what's the generalization risk? The generalization risk is just the expectation over some fresh sample from P star of the error between the observation y and the prediction beta dot x. So this, in some sense, is all standard setup so far, but maybe let me just pause briefly to check, are there any questions on how things are being set up so far? Okay, so this is what we would be trying to do. And I guess when I talk about generalization theory, not only are we trying to obtain a beta hat that has low generalization risk, but we're trying to make some prediction about what the generalization risk would actually be. So, just looking at my training data, I want some prediction of how well I'm going to do on some new, fresh test sample. So let's first just talk about how we would obtain this beta hat, though. So the kind of naive approach would be what's called empirical risk minimization, or equivalently just maximum likelihood. So we would minimize what's called the empirical risk. So what is the empirical risk? I'll call it R hat. It's just the error on the training data. So this quantity is called the empirical risk. And so the naive approach would just be to take beta hat to be the argmin over all beta of this empirical risk. Now the problem with this is that, remember, P is bigger than N, so we actually have more degrees of freedom than observations. So there's actually, this argmin is not well defined as a single point. It's like an entire infinite dimensional vector space of possibilities. And so we need to do something to rule out the kind of infinitely many solutions. And so a better approach is just to regularize or do ridge regression. So instead of minimizing the empirical risk, we'll define beta hat lambda to be the minimizer of some squared L2 norm of the parameters plus the empirical risk. So this is saying I'm not just going to care about fitting my training data. I also want something that has small norm. And I suppose In practice, we often have a fairly small degree of regularization or even a 0 degree of regularization. So in addition to this beta hat lambda term, I can define beta hat 0, which is just the limit as lambda goes to 0 of beta hat lambda. And this is called the minimum norm interpolating solution. And so this is just the function with the smallest parameter norm that perfectly fits all of the training data. That's why it's called the interpolating solution. So these are the objects that we're actually going. Yes?
Sorry, just a quick clarification question. So far you haven't assumed anything about the form of the distribution P star, right? Apart from assumption 1. So there's no Gaussianity or anything here, or
there's no Gaussianity here. I do not want to assume Gaussianity.
Oh, you don't want to. I was going to ask if it's as interesting in that setting too, or okay.
Yeah, I'm going to. I mean, it's actually not like terrible to assume Gaussianity, but I'm going to avoid that for this talk. In some sense, part of the interesting thing here is that we can get away with something much weaker, which is basically you're just going to need a certain local version of the Marchenko-Krasture law to hold, which certainly will hold under Gaussianity, but it will hold in other settings as well. And so I'll get to kind of exactly what assumption we'll need later. Yeah.
Thank you.
Yep. I guess the thing I will need is to have sort of some bounded moments. So in particular, I certainly need at least bounded second moments and probably a bit more than that. But yeah, we'll get to the exact assumptions in a bit, but that's a good question. Okay, so these are kind of the objects we're going to care about. This beta hat lambda and beta hat 0. And I guess just as kind of a useful simplification, we can actually write down the solution to this analytically. If we, it's analytical in terms of what's called the empirical covariance matrix. So if we let S hat, I'm using S instead of sigma since I already have sigma for some. If we let S hat be this kind of second moment matrix of the observed xi's, then we can actually write beta hat lambda as lambda I plus S hat inverse times S hat beta star plus these kind of noise terms, the sum of epsilon I xi. So basically, if you had no noise, then beta hat lambda you can think of as kind of like this regularized projection of beta star, right? So what's going to kind of happen here for any large eigenvalues of S hat, the lambda term will be kind of negligible and the S hat term will be large. And so you'll have sort of S hat inverse S hat. And so this is going to kind of be equal to beta star on the large eigenvalues and 0 on the small eigenvalues for kind of the opposite reason, right? Then lambda is going to dominate S hat. And so lambda inverse S hat will be very close to 0. And then kind of, you know, in between, there's going to be some decay, but you can kind of think of this as a sort of soft projection onto the span of the large eigenvalues of S hat. So that's kind of another way to think about this. Okay, so that's kind of all the setup. So now let's actually get to, you know, what do we actually want to understand? So the kind of key question we're going to want to understand here is what is the generalization risk R of beta hat lambda? So how well is my ridge regression estimator going to do? And for simplicity, for the purposes of this talk, although it's not necessary, we're going to take the noise epsilon to be 0. So actually this term here is just going to be 0. And so we are in this no noise setting. Empirically, this is actually reasonably well justified because most data sets have very low label noise. It also turns out that this is actually without loss of generality when p is bigger than n. And the basic reason why is that when p is larger than n, noise is actually information theoretically indistinguishable from having a more complex ground truth predictor. I won't go into, like, it's maybe like a 4-line derivation, so it's not too hard, but I won't go into it just in the interest of time. But it turns out that this is actually without loss of generality. And so we're just going to kind of focus on that case for now. And if we kind of perform that simplification, the risk also simplifies, right? Because then the risk is just the expectation of beta x minus beta star x, since there's no noise. And so this comes out to just be this quadratic form where S is equal to the kind of population counterpart of S hat. Right, so remember up here, we had S hat, which was this kind of empirical second moment matrix. And down here, we have this population second moment matrix. And so if I kind of combine these formulas, right, so here I have an explicit expression for beta hat. Here I have an explicit expression for R. I asked what is R of beta hat. So in some sense, this is actually a pretty easy question to answer. I'm just going to plug one thing into the other. And so what this gives me is this formula, which ends up not being too bad. So I guess first I need to worry, okay, I care about kind of this term in the formula, the beta star minus beta hat term. So a kind of quick calculation tells us that beta star minus beta hat is actually equal to lambda times lambda plus S hat inverse beta star. And so if we kind of plug all of this into the risk, I get this kind of nice expression. That has beta star and S hat and S in it. And just to kind of keep track of like what's kind of going on here, so there's this S term and this beta star term. These are fixed quantities. And they're unfortunately fixed but unknown quantities. Then there's these S hat terms, which are not fixed. They're actually random quantities, but even they're sort of random a priori, but they're actually observed because S hat is something we can compute from data. So these are random but known. So this expression has a combination of quantities that are fixed but unknown and quantities that are random but known. Generally speaking, that's not what we want our bounds to look like. You know, there's kind of two types of bounds we might care about. We either want an a priori bound that depends only on population parameters like S, and so it doesn't have any S hat in it. Or we want a empirically computable bound that depends only on S hat and doesn't have any S's in it. So we, depending on what we are kind of going for, we either want to eliminate S and beta star from this bound, or eliminate S hat. So eliminating S hat would require, say, taking like some expectation or high probability bound. Eliminating S and beta star would involve coming up with some way of somehow estimating those asymptotically from data. And so this is kind of our goal here. Basically, we're either trying to get rid of the red stuff or trying to get rid of the blue stuff. I like data, so I'm going to try to get rid of the red stuff, but I'll explain how essentially the same ideas could get rid of the blue stuff instead. Okay, so this is what we're trying to do. And this expression is basically the starting point for most analyses. So any questions here?
So yeah, maybe a quick, again, clarification. So S is the true covariance matrix, right?
That's right. S is the true covariance, or second moment matrix, but yes.
Oh, second moment. Okay. Is it interesting in the setting when the distribution is actually isotropic, so that I can assume that S is identity?
Right. So when S is isotropic, so a lot of analyses go with S being isotropic. I think that often makes the analysis a lot easier, but in some ways is, at least for me, I find it to be too simplifying because most empirical S's actually have power law decay.
Oh, I see. Okay.
I would actually be quite happy for S to be diagonal. I think diagonal S would not really change things very much, but I do really want S to be able to have distinct eigenvalues, because the fact that the eigenvalues decay as a power law turns out to be a very important feature of the problem.
Okay, thank you.
Yeah, but feel free to think of S as diagonal if you want. S hat, of course, won't be diagonal, but that's kind of okay. Okay, great. Any other questions? Okay, so let me now get into kind of some obstacles here. So there's basically two tempting simplifications to make. I'd say these are tempting, but fairly dangerous because they often end up making your bounds vacuous. And these are simplifications that get applied all the time. They're simplifications I've applied in like my past work, but I've kind of grown to want to stop using them. And so the first one is you might want to apply an operator norm bound here. Right, so I might just want to say, well, this quadratic form is kind of annoying. So let's just say I can bound this by, the squared L2 norm of beta star times the operator norm of this matrix. So the issue with this, as I'll show in about 2 minutes, is that actually empirically, it appears that beta star is infinite, and I'll kind of show the evidence for that. So that's kind of one simplification you might want to make that you can't really. Another one is you might want to say, okay, what if we could just say that S and S hat are kind of similar? Well, okay, we kind of know that's too much to hope for because S hat kind of only has rank n, and S probably has rank p, which is much bigger than n. But maybe a slightly, a slightly better thing to hope for would be that S is close to, say, lambda I plus S hat. The kind of justification for that is that, the sort of small eigenvalues of S will be dominated by the lambda I term. The large eigenvalues of S will be dominated by the S hat term. And so maybe I don't even need to say is approximately equal to, and maybe I just need to say it's kind of like dominated by. And you can even show this is actually true if n is large enough. But the kind of problem here is that if we swap S for S hat in the kind of expression for the risk, this is the same as replacing the generalization risk R with the empirical risk R hat. And so, that you could think that's fine, because if we're regularizing enough, these might actually be close to each other. But the problem is that actually R hat is approximately 0 for the kind of optimal choice of lambda. And so what I mean by that is that if you were to sort of tune your regularization strength to get the smallest possible test error, your lambda would be small. You would actually want to pick a lambda that's small enough that that the empirical risk was quite low. And so that kind of means that, well, anytime that this approximation here that we wrote down holds, would imply that the empirical risk and the generalization risk are close to each other. And so they kind of can't hold in the regime that you would most care about. So to kind of bring both of these points home, I want to show some plots. So this is where we get to the empirical part of this talk. So let's see. Did this actually work? Yes. Okay, so can people see the slide plot? Cool. So I guess this is the first thing, saying that real functions have infinite norm. So what's the evidence for this? So what I'm plotting here is I generated a linear model based on a neural tangent kernel for ResNet 18 on the CFR10 dataset. And I'm fitting it to increasingly large amounts of data. So this x-axis here is the number of, so this x-axis here is the number of data points on a logarithmic scale. And then this y-axis is the L2 norm of the minimum norm interpolating solution divided by root n. And this, I guess, this should be like a lower bound on the norm of beta star, because beta star should also be an interpolating solution, so it should have higher norm. And what you can see is that even after this normalization by root n, things are growing at a polynomial rate. The polynomial rate is about n to the 0.2. So, so basically, the norm of these parameters is growing, is super constant. So if you kind of believe that this trend continued, then you would think that as n goes to infinity, this norm would be infinite. And so in particular, the norm of beta star should be infinite. So this is kind of the first point. And so any generalization bound that depends on the norm of beta star, or even on the norm of beta hat, is going to either be vacuous or increasing with n. And note that the actual generalization error, perhaps unsurprisingly, is decreasing with n, and the empirical risk is 0. So this is kind of the empirical evidence for this first obstacle that I talked about.
And how is P growing again? So P is also increasing with n, right?
Yeah, P is like P is actually fixed here. So because this is a fixed ResNet 18, it's in, say, like, I think in the tens of millions of parameters, if I remember correctly. In some sense, yeah, so P is fixed, but like it's effectively infinite compared to the size of the data set, because it's so much larger. Cool. Any other questions about this? And how much time do I have, Aravind?
Maybe around 5 minutes, a little more than 5 minutes.
Okay, great. Okay, so then the next point is this empirical risk versus generalization risk. So I guess these solid lines are the empirical risk. So if you kind of look like their inflection points are kind of like, or sorry, they're like minima are sort of like around here roughly. If you look at the empirical risk, that's kind of these curves here. So I guess they're not like literally zero, but they're kind of like in this regime where the empirical risk is quite small, certainly small compared to the generalization risk, and they don't really converge to each other until you have a regularization strength that's significantly larger. And note this is like on a log scale. So even though these look kind of close together, this is actually like 2 orders of magnitude difference in terms of the regularization strength. And so this is saying if you really cared about kind of, this regime here, which is the sort of empirically optimal regularizer, you want an analysis that's going to work, even though the empirical risk is far away from the population risk. So this is kind of the second obstacle. Okay, so are there questions about this? Okay, so this is something that kind of was very troublesome for me. I wasn't sure what to do about it, but fortunately, I had students who are smarter than me, and so they were able to figure something out. So basically, oops. Sorry, okay, there we go. Okay, so basically, it turns out that you can kind of fix this problem using random matrix theory. So recall that we had this risk formula that was this thing up here. So I'll just write it again down here so that we have space. So this kind of has this problem that we already talked about, which is that it kind of mixes S with S hat. But fortunately, random matrix theory is kind of good at handling expressions that have S's and S hats together. And so we can handle this with what's called a local random matrix law. And so think of this as a kind of fine-grained version of the Marchenko-Pasteur law. And so this is kind of the assumption we need to make. We need to assume that our data is such that this local random matrix law holds. And it's been established under like various different assumptions that you can get local random matrix laws like this. And so if you do this, then you can show that this formula is asymptotically equivalent to a different quantity called the generalized covariance estimator, which I'll call RGCV of lambda. And what is it equal to? So it's a ratio of 2 terms. The numerator term is the empirical risk. So this might seem bad because we were saying that we want to be in the regime where the empirical risk and the generalization risk are not the same. So the thing that's going to save us is we're going to divide by a correction term, which is going to be a sum over the eigenvalues of S hat of this ratio lambda j of s hat over lambda plus lambda j of s hat. So this lambda j is just the jth eigenvalue of s hat. And so this quantity here in this sum, you can think of as basically the effective dimension of the problem. Why is it the effective dimension? It's, you know, again, if we kind of think of this ratio as rounding everything to either 0 or 1, it's kind of counting the number of eigenvalues that are much larger than the regularization strength lambda. So any eigenvalue that's small compared to the regularization lambda, this term will be close to 0. Anything where it's large, it'll be close to 1. And so it's kind of counting the number of large terms in my eigenvalue spectrum. And so in the classical regime, this would actually be equivalent to just dividing by like 1 minus p over n. And that actually is a standard thing to do. This is like a standard degree of freedom correction. It's sometimes called Bessel's correction. And so you can think of this as just sort of generalizing a very standard classical degree of freedom corrector to this non-parametric setting. And so this is called the GCV estimator. Like I said, it was actually first proposed in 1978. It was also recently reproposed by Jucot and co-authors in 2020. They call it the kernel alignment risk estimator. And they have a kind of derivation based on some Gaussianity heuristics that kind of gets the same formula. And it turns out that this formula tracks empirical performance very well. So what I mean by that is, if we kind of go back here, I can take a bunch of actual deep neural networks that were pre-trained on ImageNet. I need to somehow turn them into a linear model. So what am I going to do? I'm going to take a kind of first order Taylor approximation of them to get a linear model, and then use that as a model for various data sets like CFAR, Fashion MNIST, a few others. And so kind of this gets around the issue I brought up at the beginning, where I said, well, deep networks actually learn pretty semantically meaningful features, so we should care about them. So here, since I'm taking a pre-trained model, that model has all of the learned features. And so this kind of linearization kind of still contains all those features. It's just not allowing kind of additional features to be learned during fine-tuning. And you can kind of show empirically that hurts accuracy a little bit, but generally these models still perform pretty well on the fine-tuned data sets. And then this is just showing that you get quite good empirical fit across a variety of sample sizes and a variety of data sets and a variety of architectures. And this actually computationally, this is pretty tricky because you have to deal with kernels that have like tens or hundreds of millions of parameters in them. So I won't go into that because I think I'm basically out of time. But that's kind of the punchline. Should I be stopping now, or?
This might be a good time to stop.
Yeah,
if
cool.
I mean, unless you want to say something, yeah, you can take another minute or so if you want, but yeah.
Cool. I think the only other thing I want to say is like, I think one intuition that people often have, again, including me 6 months ago, is that generalization is primarily determined by the rate of eigendecay of the problem you have. It turns out this is not really the dominant factor in a lot of empirical settings. So this is just showing that if you take randomly initialized models and pre-trained models, the pre-trained models actually have worse eigendecay. But it turns out that somehow the like ground truth vector has better alignment with your kind of predictors, and that's the thing that that kind of leads to better generalization. Okay, so I think I'll stop there and happy to take any questions.
Thank you, Jacob. Any questions for Jacob? So maybe let me ask one question. So I was just wondering about the, so suppose you kind of, train some a neural network on maybe the data is actually generated by a two-layer neural network or something, and then you get this something in the neural tangent kernel regime, and you can fit a good linear model. I was just curious if to the training data. I was wondering if the new samples that you draw from a Dep2 neural network, do you expect them to have this kind of I guess my broad question is, can you use this kind of analysis to argue about test error when your data is also drawn from, let's say, a neural network?
Right. So I think that this is kind of a subtle thing. So if the data were actually generated by a fixed neural network, then that would mean that your parameters had finite norm, right? Because that network would have some fixed parameters, and those would all be finite numbers. And so in some sense, what this is saying is that there is no fixed neural network that that kind of fits all of the data, but that if you kind of make the like parameter values larger and larger, then asymptotically you can always fit the data. So I think if you were in the regime you're talking about, you would actually get very different rates of convergence. Like the power law rates, like it would still be a power law rate, it would be slower than root n, but it would be kind of faster than you observe empirically.
Oh, I see. Okay. I see. Any other questions for Jacob? Okay. If not, let's thank the speaker again. Let's thank you, Jacob.
Thank you all.
And thanks to Chris and all the Jacob and all the speakers in the workshop. I also just wanted to thank my workshop co-organizers, Alexander Madry and Daniel Shu, and the workshop chairs for Fox. And also special thanks to Nishit Vishnoi, who is the Fox PC chair, who was involved both in the conception of the whole workshop and planning the workshop. I hope you all have a great rest of the conference. Thank you all for coming.
Thanks. See you.